Welcome to The Explainer. Today, we are doing something really cool. We're taking a guided tour of one of the most legendary books in software, Windows Internals Part 1. Our goal is to build a quick mental map of how Windows actually works under the hood.
So right off the bat, the book itself gives you this pretty stern warning, and it sets the stage perfectly, What we're about to look at is the powerful, sensitive, and often undocumented machinery of the operating system. It's for understanding, not for trying to build your next app on top of.
Here's our roadmap for this whole journey. We'll start with the foundational split in the architecture. Then, we'll see how programs and threads actually run, how memory is so masterfully managed, and finally, how the system talks to your hardware and keeps everything secure. Each piece really builds on the last. So, let's get into it.
All right, first up, cracking open Windows. Before we dive into the really deep end, it's worth asking, why should you even care about this stuff? This part of the book is all about setting the stage, not just defining the concepts, but also introducing the incredible tools you can use to actually see these ideas in action on your own machine.
Yeah, this book is not exactly light reading. It's really written for people who want to understand the why behind the OS, breaking down these core concepts like processes and threads. And crucially, it doesn't just talk theory. It points you to these amazing tools like Process Explorer that basically let you become a detective on your own system. Okay, now we're getting to the absolute heart of the matter, the core architecture. If there's one single concept you need to grasp to understand pretty much any modern operating system, this is it. It's all about this huge protected divide between your everyday programs and the trusted core of the OS itself.
And boom, here it is. This is that great divide. Everything you interact with, your web browser, your games, everything lives up top in what we call user mode. But the real power, the core logic that actually controls the hardware, lives down below in the protected kernel mode. This separation is everything.
So why does this matter so much? Well, think of user mode as a sandbox. Your applications are isolated. They have their own private memory, and they can't just reach out and mess with the hardware directly. Kernel mode, though, that's the kingdom. It's got the keys to everything. For an app to get anything important done, it has to respectfully ask the kernel by making what's called a system service call.
Now, you might be wondering, how does one operating system run on thousands of different hardware configurations? A huge part of the answer is this thing called the hardware abstraction layer, or HAL. You can think of it like a universal travel adapter. It sits at the very bottom of the kernel, and it presents a standardized interface to the rest of the OS, hiding all the messy, specific details of the motherboard and processor underneath.
Okay, section 3. So now that we've got this two-level world, user and kernel, let's talk about what's actually living and working in it. How does Windows keep track of all the different programs you're running at once? Well, it all comes down to two key things: processes and threads. Think of a process as the house that an application lives in. When you launch an app, Windows creates a process, and that process holds everything the app needs to survive: its own private memory space, a list of all the files it has open, and, most importantly, at least one thread to actually go and execute its code. And this is where it gets really cool when you use a tool like Process Explorer. It doesn't just show you a flat list of stuff that's running. It shows you the process tree. You can actually see the parent-child relationships, which tells you exactly which process was responsible for launching another. It's incredibly useful for figuring out what's going on. So if the process is the house, the thread is the person inside the house actually doing the work. A thread is the actual sequence of instructions that the operating system scheduler sends to the CPU to execute. Modern apps use tons of threads, which is how your word processor can check your spelling in the background while you're still busy typing.
On to section 4, managing memory. Now this is where things get really, really clever. We're about to look at maybe the greatest magic trick a modern OS performs: the virtual illusion. It's how Windows convinces every single program that it has the entire computer's memory all to itself.
So how does this trick work? Well, this diagram gives us a peek behind the curtain. On the surface, a process just sees this simple, clean, private block of memory. But behind the scenes, the Windows Memory Manager is frantically working, mapping those simple virtual addresses to scattered chunks of physical RAM, or even swapping less used chunks out to your hard drive in something called the page file. If you're on a classic 32-bit system, that virtual address space was 4 gigabytes total. And look at how Windows splits it. It gives the bottom half, 2 gigs, to the user mode process for its private stuff, and it reserves the entire top half for the kernel. That protected boundary we talked about is baked right into the memory map of every single process.
And that, right there, is the bedrock of modern system stability. Because every app is locked inside its own virtual memory sandbox, a crash in your web browser can't corrupt the memory of your music player. And most importantly, it can't bring down the entire operating system. This is why we don't have to reboot our PCs 10 times a day anymore.
All right, last stop on our tour, I/O and security. This is where it all comes together. How does the OS act as the gatekeeper for all your hardware? And how does it decide who's allowed to do what? These are two massive systems, but they are deeply connected. Every single time your app wants to touch hardware, whether it's reading a file from your disk or just moving the mouse, it can't do it directly. It has to make a request to the I/O system. That system then uses these highly specialized kernel mode programs called drivers to translate the app's generic request into the specific low-level commands that a piece of hardware actually understands.
And these drivers are often layered in what's called a driver stack, kind of like building blocks. At the bottom, a bus driver is responsible for things like the USB or PCI bus. On top of that, a function driver provides the main functionality for a device. And then you can have filter drivers that sit in between, intercepting requests to add features, like an antivirus scanner checking a file as it's being read. And underpinning this entire OS is an incredibly powerful security model. The easiest way to think about it is this. Every single object, from a file to a process, has a security tag. That tag contains an access control list, the ACL, which is basically a guest list stating exactly who can do what. This is then layered with system-wide privileges for big actions and integrity levels to stop some sketchy downloaded program from messing with critical system files. Look, this tour has really just scratched the surface, but hopefully it's given you a blueprint for how all the major pieces of Windows fit together. The book is the ultimate guide, of course, but the real fun begins when you fire up a tool like Process Explorer and you see these systems all interacting live. You now have the map. So which part of the city will you explore first?
If you want to help me out, please smash that like button, leave a random comment and subscribe if you want to become a better hacker.